into the linear algebra of the theory in Chapter 3. And then this will be the last day we really have to go deep into the appendices, I think. I noticed that there is one appendix that does discuss the independence of the numerator and denominator of the F statistic. At least this is the theory behind it, and he doesn't prove anything there. He just states a couple of theorems. That's in appendix C.2.4. And then there are a bunch of calculations in appendix C3 that some of which we're going to cover today. The author doesn't really get into the distributional theory that much, except by stating that one theorem in section C.2.4, one appendix. So you won't see a lot of moment generating calculations in the appendices. But the appendices are pretty scary. So I'm just going to cover them the way I want to cover them. I am going to try to get to the general linear hypothesis today.
I misread the question. My question doesn't have any relevance.
Darn. Okay. No relevance. Well, let's see. And we're going to have an exam due 2 weeks from today? Is that what it is? Today's the 19th of June, then we have the 26th of June, and then we have the 3rd of July. Okay? So someone said they had to...
No class.
There is class. 4th of July, there's no class.
No, it says on the
really now?
There's no class on the 3rd. So that's what they said for my class anyway. It's really confusing. I've heard both.
I don't believe that is true.
If you tell me there's class, that means I'm allowed to have class on that day too, which I really need that extra day for algebra.
Well, I will check that after where it's done. How about if we just make it due on July 5th? Okay? I don't know if I have another homework due on that day. Let's see, do I? Well, no, I don't. I do not have. I have a homework due on July 6th. So why don't we just make the exam due on July 5th, and that'll cover all bases. Now, therefore, I probably won't give it to you till a week from today. Okay? I'll give it to you a week from today. I'll make it available online. I know there was a certain request to have it made by Thursday this week, but I think that I'll make it available on Monday. Okay? And then you can ask questions by Thursday. Hopefully, there'll still be ample time. And if there is no class on Monday, July 3rd, fine. I'm sure everybody will be happy. But as far as I know, the only day that's a holiday is July 4th, and that's the way the schedules were made. So let's just check that, recheck it, though. Maybe somebody made a change. Okay? Maybe it's been updated. Okay. So, no big deal. What I will do, and that is, if there is no class on July 3rd, that'll be fine, and then we'll have a class July 24th, and the exam will be due on the July 26th. Okay, I'd already given you an extra day to turn in the exam, the final exam anyway. And if people are going to be going out of town and so on, please plan accordingly. Sorry for that. Okay, so there will be a class on July 24th. Yeah. No, I think that's a mistake, that there is a class on July 3rd. But in any case, we will have a class on July 24th since I'll be gone the week preceding. And I figure I'll have to catch up on office hours for a couple people anyway. Other people might say, I'm done, That's fine, If you want to try your exam and go. Okay. So, that exam will be available, obviously, before I leave, okay, with enough time so you can ask questions before I leave, too. So I'll try to make that available. The Monday, that's going to be July 10th, I guess, then. Okay. It ends quickly. Okay. Let's go on. We have, in Chapter 3, what we have is a bunch of regression calculations, a bunch of examples. We're going to mostly focus on the delivery time data. There are a lot of calculations to do the general theory. So I'm going to try to skip through some of it, give you the main highlights. Okay? So let's go back to where we finished last time, which is calculation of the estimate of sigma squared in multiple linear regression. going to try to split this board down the middle. Okay, so it's going to be obvious where to read on one half or the other half. Okay. Let's see, what did we do? We calculated, what do we have? The summation, we have y equals x beta plus error, okay, is our model. X is n by p, p is k plus 1, k equals the number of regressors. This is with intercept, that p is k plus 1. Because the 1 is the first column of x. So x looks like this. It's a column of 1s. It's then x, 1, 1, x, 2, 1, and so on. The second index is a 1, xn1. Okay? That's the first regressor. You have n x values. Right? And then you have a second regressor. You have n more x values of a different x, different variable x, 1, 2, x, 2, 2, down to x, n2. And then, of course, in the general situation, you've got x1k down to xnk. So n you think of as big and k as relatively small. Okay? This is n by k plus 1. And, of course, many of the illustrations, if I want to illustrate something, I'll just take k equal to 2 to show the multiple case. Questions about this? Yeah, you're looking concerned.
I got it now.
Okay. All right. So P is the number of columns here. And we're going to assume that the column space has dimension P. So we assume that dimension of X is equal to P. We normally think n is bigger than P. Okay? If n is too small, then this doesn't work. Okay? If n is less than P, then dimension can't be P. Okay? Okay? Remember that from linear algebra, the number of linearly independent columns or linearly independent rows. But we're going to sort of think about it in terms of linearly independent columns. The dimension is the maximal number of linearly independent columns. We assume that all the columns, we assume that the columns do form a linearly independent set, therefore. Okay? Okay, now what is EI? EI is, what you do is you calculate beta hat, which we did before. Beta hat turns out under the assumption that X has this full column rank, then you can calculate beta hat by this formula. Beta hat is x prime x inverse x prime y. Okay? Got to make sure they're the right dimensions, because x prime is what multiplies y. I have to put x on its side, okay, in order to make the product with y. Y is long. Y is long, again, y1 down to yn. Okay, so xy doesn't make sense. X prime y makes sense. Is everybody kind of following that? Maybe I should make this really long, okay, to make it clearer how that goes. Well, anyway, I can't stretch it out easily on the board here, but this is long, okay? So in order to multiply y, this is n by k plus 1. Y is n by 1. I can't multiply this times this, right? It has to be the k plus 1 by n that multiplies this. Keep your dimensions right. It's like keeping your physics units right, okay? So in order to keep straight track of the formulas. Oh, there's 3 x's and then there's a y. Okay, well, all right. Well, no, we'll get a little bit better than that. So this is a p by p. This is p by n, and this is n by 1. So that gives you a p by 1 when you multiply it out. Keep track of these formulas, which is correct. So beta hat, which is otherwise known as beta 0 hat, beta 1 hat, down to beta k hat. All right, those are the intercept and the various slope parameters in the model. So everybody, writing this out in full, of course, this means that beta 0 x, excuse me, that beta 0 1, if I write this out in vector notation, because y is a vector here, it's an n by 1 vector. Beta is a p by 1 vector. Epsilon's an n by 1 vector of errors. So writing it out in vector format is beta 0 1 plus beta 1 x1 plus and so on plus beta k xk plus epsilon. You have to be somewhat fluid with these different formulas. All right, and of course then generally you'll just write for the linear regression equation y equals, the author write y equals beta 0 plus beta 1 x1 plus and so on plus beta k xk without all the arrows on there plus epsilon, and so it's just eliminating the index I in essence. All right, so that's what we do. That's the least squares estimate of beta, of the betas. We call that the least square estimate. And then we had E equals y minus x beta hat. Okay, that's the actual difference. So EI, what this means, if you write it out, is that EI is equal to YI minus beta 0 XI1, beta 0 hat minus beta, plus beta 1 hat XI2 plus and so on plus beta K hat XIK. So that's the actual definition of the ith residual, which of course are being automatically computed for you. And we're going to do residual analysis pretty much for the rest of the course after today. Okay, we'll start that on Wednesday. Which is the fun part, just looking at pictures, trying to interpret what's going on. Now, that can be written out in short form, though, as y. So we need our linear algebra tools to make writing short y minus x. Beta hat, we said, was this thing. So it's x prime x inverse x prime y. Okay, so that can be multiplied out as y. And now I'm going to leave the arrow off the y. I minus h. I'm sorry, I minus, the y comes over here. Okay, this is an n by n matrix. This x times, even though there's a little matrix inside, this x is not on its side. Okay, this is a tall matrix, there's a little square matrix, and there's a sideways matrix here. So this is an n by n matrix in here. So this x, if you want to think of it in terms of blocks, this h is formed like this, then there's a little square block in here with an inverse sign on it, and then there's a long, I need a long one, this way. Okay? Can't really see the length of that. Let me make it longer. This one here, minus one, and then longer this way. Okay? And that makes an n by n. This is x prime, this is x, and this is x prime x, and then inversed. Okay? So that's your H matrix. And we did mention that it is a projection matrix. H squared is equal to H. It's symmetric, and its square is equal to itself. Okay. So this is y minus projection of y onto the column space of x. The reason I'm going through all these dimensions and so on is just, if you really want to study this, it just makes it so much more efficient to understand. Keep in your mind's eye what these things are doing. Now, what is then the sum of this? We went actually through this a little bit last time, but I'm reviewing it. This is the SS res, the sum of the squares of the residuals. I could go ahead and calculate it term by term, or just, just take the sum of the squares from the residual output from Excel. You're going to calculate the residuals in multiple regression. Done it 100 times already for the simple linear regression model, right? So just add them up. Add up the squares, that is. Add up the squares. And here, though, I want to actually calculate what the expected value of this SS-res is to show that, to recall what we had for that. So let's see. What is that, though? Therefore, that is simply the norm square of the vector E, which is written down as the norm square, therefore, of I minus H times Y. Now, how do I do norm square? Well, I take the transpose of the vector and multiply it times the vector as a matrix product. So in other words, if I want to take the square norm of a vector V in Rn, I can simply write that as V prime V. All right, that gives it a 1 by 1. All right, that's a 1 by 1 vector now. I mean 1 by 1, matrix equals the square. So this comes out to be therefore I minus H times Y prime it times I minus H times Y, which is then take the transpose of the product in reverse order. You got to get fast to this. Now, what is the prime of I minus H? Well, I is symmetric, H is symmetric, so that you get I minus H back again. I minus H, and then Y. Okay, so let's take that up here now. Now multiply this out. You get I times I minus H times I, which is H, minus I times H, which is H, plus H times H, which is H squared. But we said that H squared is equal to H, so-called idempotency. So we have that this is equal to Y prime times I minus H minus 2H plus H squared Y equals Y prime I minus H Y. Yeah. Hi, Lindsay. We moved to this room. Thank you for finding us. Okay. I'll mention at the break the announcements I made in the class. Okay. So, that's a little formula for the sum of the squares of the residuals. Okay, for SS-res. You don't have to memorize it. Okay. It's just kind of going through the calculation. Then what did we do? All right. We actually did this, and then I guess I take it back again. Then I write this as Y prime Y minus, maybe this is a faster way to do it, minus, I'm going to go ahead and now put the x's back again. X prime X inverse, X prime Y. It was just I took the x's out to make the calculation less messy with this H. That was the point of using the H. Because otherwise you got x's flying all over the board. Everybody's like, ugh. Okay. It's messy. So, then what do you have? Well, this is beta hat. So if I actually want to do that, then this is Y prime Y minus Y prime X beta hat. Okay? X does multiply beta hat. Okay? In fact, X beta hat is Y hat. Okay? The vector of predicted. So this is Y prime Y minus Y prime Y hat. Okay? So you take the square of the Y column, and then you take the product of the Y column on the predicted. Okay? So that's really, if you want to think about it that way. All right? Now also, this is scalar. Both of these terms are scalar. Right? So I can always rewrite the scalar in terms of, I can write it as this transpose of itself. Okay, so this is another way to write this, is Y prime Y minus beta hat prime X prime Y. Bring the X prime Y back in. Okay. Generally, that's how it's done. Okay. As a convenient formula. So that's SS-res. That's the formula for it.
Doesn't it? Oh, that's a 1 by 1, so you can't just say it transposes itself. Okay.
Yes, I can. The transposes itself. This is a 1 by 1.
Yeah.
That's what I'm doing. Okay, that's a 1 by 1, so I'm taking the transpose of it, saying it's equal to itself. Okay. So this is a formula for SS res. Last time we showed that using, I guess, this formula back up here, okay, y prime I minus h y, what the expectation of SS res was. So last time we showed, I'm not going to go through it again. I'll probably have to do it again, something like it again today anyway, that expectation of SS res is equal to p sigma squared. Okay. Therefore, sigma hat squared equals to SS res divided by p is unbiased for sigma squared, and that's, so you can calculate it this way, and you can calculate it this way. I'm sorry. Yes, n minus p. N minus p.
Don't confuse me now.
I won't. Too much. Okay. I got something else on my mind. Okay, yeah, you got to keep track of the n minus p and the p. Yeah, so if it has, if it's the sample, I think in the delivery time data we had 25. In fact, here's the very next line in the notes. In the delivery time data of example 3.1, delivery time data I said twice. Okay, n equals 25 and p equals 3. And I do believe I divide by the correct number 22 later in these lines on page 1 of these notes. Okay? Yes. Okay. So let's go ahead and look at that. So let's look at the example 3.1. I believe that the calculations are shown on note 3 where I did the Maple worksheet. If you have note 3, you could pull that out. But I pretty much copied from that. We had n equals to 25 and p equals 3. Two regressors. Not only did you take the number of cases that were being delivered, but some kind of distance that they needed to be hauled somehow. And there's the issue of servicing the machine, which is one of the things I graded on for the intercept question of this most recently graded homework. Yes?
I have a question on that one. The residuals to me looked really bad because they were heavily weighted, like for the zero intercept model. Like there were 8 points above 0 and like 20 points below 0, which to me, like, granted the ones that were above were like way out there.
Yeah, there was some slight problems with the no intercept model in that.
Okay.
For the simple linear regression problem, it looked like there was a downward trend even to the residuals when you forced the no intercept model. Okay. So, but it wasn't that dramatic. Okay. Problem with the residuals in that. I think the point was, and you were supposed to look at the bottom of page 49 of the text, they told you that we want to study whether the MSE has MS res, whether the mean square for residual was decreased or not, for the no intercept model, and it was. So, and you mentioned something about R squared being bigger for one of the models. But I've really, it's not quite equivalent. It turns out R squared can move around. Okay, with the no intercept model, R squared can be screwy. Okay. You're going to do some R squared. They're all high R squareds. They were 93%, 95%, and so on. But the change in MSE was non-trivial. It was something like a 20% change. I keep calling it MSE. It's MS res. I sometimes say MS. This is also called MS res, and in other books it might also be called MSE, mean square for error. Okay, which is the traditional one. But for some reason in this edition, I guess it was requested by some of the critics to call it res. Okay, or maybe it was his own critic. I'm not sure. Okay. Residual mean square and or mean square for error. Okay, that's the sigma squared estimator. All right, there was actually a 20% drop in that, or something like that, for the with intercept model as compared to the no intercept model. So I think as I recall anyway, there was some kind of issue there. So that I wanted people to catch. So it was good to look at R squared. Everybody did pretty well in the homework. And I think I graded off a couple points on everybody. But that was about it. So what happened in the delivery time data? You got a beta hat, so there's three estimators, 2.3412, 1.6159, and 0.0144. The actual numerical values, just because this is small doesn't mean it's necessarily not acceptable, because we're not, I mean, the units may be funny. Just because this is a small coefficient doesn't mean it's negligible. Okay? It looks like it has more zeros in it. Okay? Doesn't mean that, though. Okay? Doesn't mean it's negligible. We'll discuss that later. And x prime y is also a 3 by 1 matrix. Let's just go ahead and write it down, just so you see what this formula is doing. There are relatively small matrices here. That's probably traditionally why these particular formulas were used, because there wasn't a whole lot of machine calculation. It was calculator only, or pencil and paper. So there are some small matrices, okay? And then you go ahead and you take y prime y minus the inner product of this one with this one. Okay? So beta hat prime, x prime y, came out to be just that number 2.3412 times 559.6 plus and so on, plus three terms, 0.0144 times the 337,001, okay, equals 18076.90, and so sigma hat squared is therefore the difference between the 18310 and the 18076. Divided by the number of degrees of freedom, which is 22. The 25 minus 3. Okay? Which is 22. And so you get the SS res was 233 for the two regressors case, I believe. We're pretty familiar with this data by now, aren't we? Actually, did you have to do a homework problem with this yet? The delivery time data?
No.
No, you didn't have to yet. I think maybe it's section 3.5. Is that what it is?
Didn't we do something in chapter 2, one of the ones? It wasn't the multiple.
No. Did you do simple linear regression on delivery time data for today?
I think we did.
No, you did maybe you did it with engine displacement. Yeah, you didn't have. This is the one that's been used over and over in the book. This is the delivery time data. He's going to refer to this. The authors are going to refer to this a million times. Okay. Okay. So you might actually almost memorize the analysis of variance table. Okay. One note here, and that is, why do we calculate it this way? In simple linear regression, didn't we do SST minus SSR and then divide? This is a little bit different, because this is not SST. SST was y prime y minus ny bar squared. No. SST equals y prime y minus ny bar squared. And SSR is y prime y hat minus ny bar squared. You can actually go through the calculation. So, which is just this beta prime x prime y minus ny bar squared. So if I take the difference of these, I get exactly the same thing. What's happening is the ny bar squareds cancel. All right? So when I subtract these, I get y prime y minus beta hat prime x prime y. Okay? So that's another way to get SS res. All right? So that's in the analysis of variance table for delivery time data, this comes out to be equal to the difference of these two things SST minus SSR. If you actually look at the analysis of variance table, which is given in the text, I'm not sure which page it is. Example 3.1. 80. Thank you. Let's see. Yeah, here he gave it the SAS version. Okay? He has model, error, and corrected total. See how the different language of the various packages? Minitab versus SAS versus some other ones. So C total, that makes sure that you know that the total sum of squares is corrected by subtracting the NY bar squared. Alright? That's the so-called variability of Y. SYY is the corrected total. This has 24 degrees of freedom. That's the 5784. Okay? That's the 5784. 0.54 minus the model or regression sum of squares. He calls it the model sum of squares in this one, SSR. All right? Which again is this thing. Okay? Again, corrected. So that is 5550.81. And so then it gives you the SSE also, the same formula. It comes out 233.73. Okay?
Repeat what you said. The C total is.
This is the SST, which is this formula. SST, the reason they call it C total, because some people call the total sum of squares summation yi squared. C total would be summation yi squared, though in some terminologies, in C total would be summation yi minus y bar squared. I goes from 1 to n, which is summation yi squared minus ny bar squared. That's an identity. All right. And that's, which is y prime y in our vector notation, minus ny bar squared. Okay? So, and this is what we just called the variability. We also called this SYY. We had so many notations for this SYY. We also called it SST. Okay? The variability in Y. Corrected for the mean. All right? And that's why they call this C total. Right? After you go for a while in this subject, they just don't want to talk about. They want to say corrected for the mean after every, phrase. Okay.
But in our book, SST generally means the corrected total.
That is correct. This is correct. This means the corrected total. If I want to indicate the uncorrected total, I'll put it like a prime or something on it. So in our text, SST is the corrected total. Okay? Is everybody with us? They just call it SST. Again, for that reason, they don't want to always say corrected for the mean. This is pretty standard.
Can I just review what you just said? Like, you subtracted the C total to the SSR.
SSR, model sum of squares, or regression sum of squares. We call it in our book the regression sum of squares. That's not the same thing as the y hat beta prime x prime y. This is uncorrected regression sum of squares. Let's draw the picture. The usual picture I'm drawing here, which is the model for means. This is a set of all x beta in RP. Okay? Which would be three-dimensional subspace of, is a column space of x. Column space of x. As a subspace of Rn. So it's a high, it's not real high dimensional, but it's three-dimensional if p equals 3. If there are 3 columns of x. In simple linear regression, it really was just a plane. Okay? So then I draw the vector y. I indicated the projection of y onto this column space, the orthogonal projection, and that's known as y hat. But it's also what you have is that the beta hat are the coordinates of the this vector, this projection, in terms of the basis given by the columns of x, right? The columns of x. X beta hat is beta 0 hat times the first basis vector of the column space of x plus beta 1 hat times the second element of the basis of the column space of x, the first regressor, right? The intercept regressor, the first regressor, and so on. Then you have the kth regressor. So you have the beta hats in this version in this picture are the coordinates in terms of the basis given by the columns of x for this subspace of Rn. Remember coordinates from linear algebra?
Not at all.
You don't remember anything from linear algebra. Okay. So the words just flying through your brain at this point?
No, it's all good. It's like it.
All right, so coordinates. All right, so they're you need to get the right linear combination of the columns of x, right, to make the element of this space. And so those are the betas in this case. All right, so that's what we called hy also. All right, that's the projection. So I just apply h to y, and I get it. All right. Now, where were we going? Okay, corrected totals. There was this one vector, namely the span of 1 was in here, right? This was the vector 1, okay? It was one of the vectors in the subspace. And what I do is I can also project onto that, all right? Because that's the basic model. I'm always going to be trying to if I really wanted to just do a trivial thing, that is try to predict y from one number, okay? I would take the mean of the y values, right? And so that's what I would predict. I would predict every y the same, okay? So this would be y bar times 1. So and so I actually have projection on there too. Okay, so then you have this right triangle here business. Okay, so actually this black line that I'm drawing right here is not the projection of y onto the column space of x. It's
the difference between the projection onto the space and the projection onto just
the line.
So that's the average there.
Yeah. So this difference is what this one is. So this is y hat minus y bar times 1 is what this vector is right here. Okay? I guess I could put an arrow over this y hat thing. Okay? All right, to make sure there's a vector. This n by 1 vector. So it's this vector in this plane minus this simple adjustment. Okay, which is actually, so what I'm taking is y. I'm taking and this is what we called and so that the length of that side is the model sum of squares adjusted for the mean, because y bar is the mean of y hat. Okay? So it's the variability of the y hats. Okay, so SSR equals summation, which is the square length of this thing, y hat minus y bar times 1. Okay. This is the model sum of squares or regression sum of squares. Okay? Which is the variability summation y hat sub I minus y bar squared. Y bar being the mean of the y hats, turns out. Okay, that just came as a consequence of the normal equations. That the average of the y hats is indeed equal to y bar. So this is the total variability of the y hat. So I could call it S sub y hat if I want. Okay? have yet another notation for it. The variability of the y hats, which is the y hat, summation y hat squared minus ny bar squared. And the y hat squared, it turns out, is the same thing as y prime y hat. Okay? So the inner product of y hat with y hat. See, look at that. The inner product of y hat with y hat, okay, is the same thing as the inner product of y with y hat. Why should that be? Well, because y is y hat plus this error here, okay, and the error inner product y hat goes out, right? So y hat inner product y hat equals y hat plus error inner product y hat, because the error is orthogonal to y hat, all right? But y hat plus error is y, equals y hat, okay? But it's not equal to y, okay? It's not in the inner product of y with y, okay? So, anyway, so this is what we call beta hat prime x prime y minus ny bar squared, okay? So it's the model sum of squares corrected for the mean. He doesn't call it C model, though, in the SAS output. They just don't do that. All right? Is everybody happy now? Does they sort of know these formulas? This picture tells pretty much everything. Okay? You're using this triangle out here. All right? Not the main triangle in the back of the board, but the one that's in the front here, in the face of the board. Okay? Because you're always going through this correction business. All right? That's the way it's done. All right. Let's go on. That's page 1 of these notes. So, he does have this picture. It's just not quite as detailed as this, right? The author does have this picture on page 81. He has x beta shown as a general element. So if you look on page 81, you have, he's got y hat equals x beta hat written in there. And then he's got x beta as a general point in the plane. So that's just point B is just a general point in the plane. Just he's indicating with that yes, indeed, the plane is the column space of x. Because he doesn't have very much notation there on that picture. Okay? So he's showing with point B is supposed to vary in your mind along the plane, the column space of x. Then he's saying, point C is the point in that plane where it minimizes the distance to y. The point in the plane that minimizes the distance to y. And that's all he's got in the picture. Okay, he doesn't have y bar times 1 or any of that other stuff in there. All right. Okay. So that's the geometrical interpretation of least squares. It's a nice picture. All right. So let's get to the analysis of variance tables. How about confidence intervals? Let's say I need to say something about the normality theory. And here's where we refer to the appendices. And then we're going to just go off the deep end after that. I'll teach you a little bit. Just a little bit. So, mainly, you've got more than one t-statistic. When you have these betas, before you did have beta 0 and beta 1, but mostly you focused on beta 1 before. And you had a couple t-statistics and so on. We didn't talk much about it. But now, with multiple regression, you've got a t-statistic for every beta. And how can you actually interpret those things? That's going to be important when we get to Chapter 9, which isn't going to be very far from now, okay, another couple of weeks. Okay, so we need to know what's going on there. So confidence intervals, let's review this theory one more time, since we've only been doing this a week, for individual regression coefficients. what we're doing is we're kind of reviewing what we did in Chapter 2, only we're doing a little bit deeper because we're actually covering the full linear model. Okay? We can't make all the equations explicit, that you have to use the matrices. So what we showed before, we showed that the covariance of beta hat, this is the variance covariance matrix. We had a nice little formula for how to calculate the variance covariance matrix, that we showed that it was sigma squared times x prime x inverse. And we actually showed how that matched up with simple linear regression last time. That the variance of beta 1 hat would actually be sigma squared over sxx. If we actually go ahead and compute this. This is a 2 by 2 matrix in case of simple linear regression, because that's p equals 2. This is a 3 by 3 in case p equals 3, which is a 2 regressor case. All right? So you can say it's, and then of course this comes out to be, what it comes out means the variance of beta hat, the variance of beta 1 hat, and the variance of beta 2 hat along the diagonal. Okay? And then on the off diagonals you have covariances. Covariance between beta 0 hat and beta 1 hat, etc. Okay? Off diagonal covariances. Covariance between beta 1 hat and beta 2 hat over here. Okay? That's what it is. And then we also write this as sigma squared times c. Alright? Where the elements of c are the elements of the x prime x inverse matrix. So this covariance matrix is given this way, is written as sigma squared times c. Where c is, he calls it capital C. And we actually computed that with the maple sheet last time, or at least I gave it to you. And Shane showed us how to actually find these products and inverses using the special array formulas in Excel last time. And we'll do some more of that today, I think. Just to remind you to do it, because I think it's kind of useful to be able to do those matrix calculations.
Either that or start doing the homework in MATLAB.
Something like that. This is actually, seems easier than MATLAB to me, because it's just so much straightforward. Okay. Now, how would I actually calculate the covariance of okay, what's the theory? The theory is that any linear combination of the elements, so if I take, is independent of sigma hat squared under the normality assumption. Assume epsilon I NID 0 sigma squared, the normality assumption, as before. Then any linear combination A0, I'm just going to use coefficients A instead of C, to not confuse with this capital C matrix. A0 beta 0 hat plus A1 beta 1 hat plus and so on plus AK beta K hat. That's a linear combination of these beta hats as random variables. Okay? Repeated sampling of the y's given the x's. Is statistically independent of sigma hat squared. Okay. We say that the whole vector beta hat is independent of sigma hat squared. But since we're not really going there of independence of vectors, okay, in general, I'm just going to write it this way, okay? And this is equivalent, actually, to the independence of vectors under the joint normality assumption. So that's all we really need here. And, in fact, then, you know, under this normality assumption, sigma hat squared is going to be a appropriately normalized chi-square random variable multiplied by sigma squared with a scaling factor sigma squared in it. Sigma hat squared. And sigma hat squared is sigma squared times, let's see if I can get it right, chi-square nu divided by nu, where nu equals n minus p, right? Was the number of degrees of freedom of sigma hat squared. Okay? Statistically independent of sigma hat squared. Statistically, is normal, also is normally distributed, because it's actually a linear combination of the y's. So that actually, okay, and it's statistically independent of sigma hat squared, and sigma hat squared is like this. Okay, so actually that's all we need to know. That's what we need to know from the normality theory. Okay, and reference is Appendix C.2.4 if you want to look it up, I believe. Some more of that. There is some of this stuff in there. But mostly it's just stating theorems. It says background from the theory of linear models. So instead of calling it this course, you call it the theory of linear models. There are other books you can look at. I think Graybill from Professor Ford Collins has all this stuff written down in his book, which is nearly encyclopedic. But it's all there, you know. He's got some good stuff in here. So he starts with a normal vector and he says some things, some theorems. So that's the basic background. It's only 3/4 of the page to state the theorems. I know not everybody's going to do that this summer, but you might think about it some other time if you take another statistics course. Okay? So we need to only know then how to normalize the beta, you know, this linear estimator, you know, in order to get a t-statistic. Because for a t-statistic, I need sigma squared z over this sigma squared chi-squared nu by nu with a square root sign. So for the t, remember, is sigma z over the square root of sigma squared chi-squared nu over nu. Okay, that's what my t-statistic is. That's t with nu degrees of freedom. Okay, that's how a t student random variable is defined. So I just have to know how to normalize this estimator to make it sigma times z. So what I really need to do is calculate the variance of it. So this is what it boils down to. So what's the variance of a0, b0 hat plus and so on plus ak, bk hat? That's what I need. I already know what the mean is. The variance equals what? The mean I already know is the mean is, because it's a linear combination, the mean is, and the beta k's we already showed were unbiased. I did that last time. Unbiased. E beta 0 hat is beta 0. E beta k hat is beta k. So this came out to be A0 beta 0 plus and so on plus AK beta k, since E beta hat equals the beta vector. Term by term, the estimators are unbiased for the corresponding parameters. This is last time we showed this. So the expectation is fine. And then the question is, what's the variance? All right, how do you do the variance of a product of a... How would I do the variance of this if I know that? This variance covariance matrix. I already know all the possible covariance between the betas and blah, blah, blah. How would I do this thing? This is a little exercise for us today, at this moment. How would I handle such a thing? What was the little handy-dandy formula I had last time that I thought everybody grokked, but I'm not sure if anybody remembers at this point? The covariance of A times Y. This is an M by N matrix, and this is an N by 1 vector. This came out to be A times the variance covariance. This is a variance covariance matrix. When I write capital C and it's a vector in there, then it means variance covariance matrix of this vector. This is a vector. And everybody says, I don't like that. Vectors in the variance covariance matrix. This is the formula we had last time. This is the handy-dandy computing formula.
Was it 5?
Yeah. Let's see. Let's check it out. This has to be an M by this is an M by 1 random vector. It's linear combinations of the y's in each row. Okay? A11, Y1, A12, Y2, and so on. A1N, YN. That's the first random vector. All right? Then you have a second one and so on down. M of them. There's an M. There's M entries in this random vector, just like there are P entries in this random vector, and you get a P by P matrix for the variance covariance matrix. Therefore, this is an M by M matrix Okay, this is an n by n matrix, assuming that y was a random vector of n variables. This was m by n. This is then n by m. So this is the right formula in terms of dimensions. Okay? That was a handy-dandy formula. Now this is a scalar, but it's a linear combination of those. So the way I can do it is it comes down to be the variance of A0, A1, AK times beta 0 hat down to beta k hat. Okay, like that. That is a product. I know the variance covariance matrix is the betas, because the sigma squared times x prime x inverse, where we used that trick last time. Now I'm going to use the trick again. Okay, so this will therefore be, just take the A0, A1 vector up to AK, and then times the variance covariance matrix here, which would be sigma squared times x prime x inverse, and then take the A0, A1 down to AK, back again like this. Okay, so that would be a formula for the variance of this linear combination of the betas. Now I'm going to take a very special case. Just take the A's so that one of them is 1 and all the others are 0. And then I will obtain the variance of beta j hat. Therefore, well, we're just going to come out to the diagonal element here. I wanted to show this more general thing, because I want to go back to this trick again. Okay, I know maybe too much to ask, but I guess I have my pet peeves. And I mean my pet desires, let's put it that way, to do certain things, to make you learn certain things. Okay. So now if I take I equal to 0 for I unequal to j and aj equal to 1, okay, then you simply get the corresponding element of diagonal element of this matrix. Then you get the variance of beta j hat is simply nothing more than the sigma squared times the times what we call, we called it, sigma squared times cjj. Okay, which is, in other words, if I take 0, 0, and so on, 1, and then 0, 0 times sigma squared times, I'm calling the inverse of this matrix capital C, and then I put 0, 0, and so on, 1, 0, 0. Okay, that's what I'm getting. This is the variance of beta j hat. Okay, from this context. Then I just get a diagonal element, right? And then what we're doing, we're calling this, what we're calling the diagonal elements of C. We're calling C, the way it's done is it's going to be C00, C11 down to CKK, because this is a P by P matrix where P is K plus 1. So that's the way we're calling it. So the diagonal elements are C00, C11 down to CKK. All right.
Are you trying to find just the variance of J?
I'm finding the variance of this linear combination for, I know, I'm trying to do two things at once, because I could have gotten this immediately from this matrix, okay? But I'm showing you how it fits into this more general situation. That if I wanted to find the variance of any linear combination of the betas, then I would calculate it this way. Right? For now, for the case where I just want to calculate the variance of one of the betas, I calculate it this way. All right?
What is a condition where you would actually want to find out the variance of a linear combination?
Okay, that's one. Okay, the way it's going to be done is in that confidence interval for the mean response. Where I'm going to take A0 equal to 1, A1 equal to X 0, 1, and so the application is going to be application is the mean response. Mean response, estimating mean response. Remember how we did confidence interval for the mean response? Confidence interval for mean, or estimating slash confidence interval. Let's put a confidence interval for mean response. So we're going to have, what I'm going to do is I'm going to take that EY given, what I'm going to do is I'm going to give a new value of X, 1 through XK. So I'm going to give you X, and the new one is going to be X01, X02. So I'm going to give a new value, so I'm going to call it the 0th observation. Okay? 0th observation of the X's. Okay? So I have K regressors, so I have to give K X values. One for number of cases, one for the number of feet the person had to go. Right? That's 2. And then however many regressors you have. Alright? So I have to give the number of cases and the number of and the distance in feet. Alright? For some new situation that hasn't been encountered yet. Alright? But I just want to get a confidence interval for the mean response. Alright? Which is beta 0 plus beta 1 x01 plus beta 2 x02 plus and so on plus beta k x0k. So that's the mean response with the betas in there. I estimate that with the beta hats. So then the estimator, the unbiased estimator, is beta 0 hat plus beta 1 hat x01 plus and so on plus beta k hat x0k. So now you have the situation where the A's are given by 1, x01, x02 up to x0k. So that's exactly the situation shown in page 103. Confidence interval estimation of the mean response. Where you've got a vector x0. Instead of calling it I do have a pet peeve about this one. Actually, the word peeve is going to come in correctly this time. And then he writes this as a column vector. He writes x0 as a column vector. x01, x0k, whereas it should be a row vector. It should be a new row of the X, capital X matrix. He writes it as a column here for some terrible reason. I don't know. But anyway, he does. Anyways, it's a mess up as far as my notation would go. So what this is really it's really just a new. If you put it on its side, I prefer it this way. On its side, x0 prime equals 1 x01 over x0k. It's another row of the capital X matrix. It's a new row of the capital X matrix. That's what it is. Anyway, live with his notation because it's in the book. It's just a matter of keeping it straight, what he's talking about. So naturally it would have been y hat equals x0 beta hat. He's got x0 prime. Alright? So this is your y hat. That's going to be the center of your confidence interval. Right? We did this before. And now I need to know what the standard error of that y hat is. Right? What's the standard error of it? Well, it's going to given by this formula right here. That's going to be the standard error of y hat when I replace sigma squared by, the square root of this is going to be the standard error of y hat, where I replace sigma by sigma hat. Okay? So the standard error of this y hat is therefore y hat given x01 through x0k. All right. We'll just put it that way. The y hat for the given new situation, okay, is therefore equal to sigma hat times the square root of what? It's well, the way he's got it here, he's got x0 prime c x0. Okay, I put the sigma hat out front, and this is my C matrix, capital C. This is what I call capital C here. Just this part. It doesn't depend on sigma, right? All right. So that's what he's got on page 103. He didn't write it as C there. He kept it as x prime x inverse. Okay? So that's exactly the formula I'm referring to. Okay. So I think for the delivery time data in your, one of the delivery here in the delivery time data, he's taking therefore the 1. He's going to try to estimate the mean response for a situation where there were 8 cases and the delivery person had to go 275 feet. So he's going to put in, for example, sigma hat times 1, 8, 275. Then you have this 3 by 3 matrix, which is the inverse of the x prime x matrix, which was calculated. It is displayed, though he doesn't say it, on page 79. Okay? He does refer to the capital C matrix, but he doesn't actually write it down except on page 79. He's got it in the calculation and the second line of the display, page 79. So C is actually equal to this 0.11321 and so on.
Page 104.
He doesn't have it on 104, which is a little bit after the fact. Okay. All right. He does put it on 104. There he is. Okay. He does finally put it there. He still doesn't call it capital C by name, though, which is kind of a pain. It'd be nice if he wrote it down somewhere. So he's got it on 2 pages, 79 and 104. Etc. There's this 3 by 3 matrix on the 1, 8, 275. So there's a thing that just depends on numbers that were given in the x values. So all this stuff depends on x's, okay, that were given, and then there's your sigma hat in front of it. Okay? That's the estimate of variability of the y hat. Okay, and you just have to multiply that by a t percentage point, and you get the plus or minus part of your confidence interval. Okay? Yes?
You were just like you're telling us, so the 18275 is the x prime.
Yeah, this is the x prime, and this is the x0, the way he did it. Okay, x0 prime. x0 prime is a sideways vector, because, I mean, he's using the default idea that a vector is always a column vector. But here, he should have broken that exception, because this is really just a new row of the capital X matrix. So this would be in the first column of the capital X matrix. That would be in the second column of the capital X matrix. X0k would be in the in the last column of the capital X matrix. All right? But anyway, it's just, again, a pet peeve of mine. All right? It's not that big of a deal. But you got to beware of it, okay? To follow the notation. All right. I think it's better to make these observations to help you get through all the formulas, because there's a lot of them. Okay. All right. So that was the application, and so you get the confidence interval, the 100 times 1 minus alpha. I might as well finish this percent confidence interval for mean response. is therefore y hat plus or minus the t alpha over 2 nu. I can't remember. In one text, they put the degrees of freedom before the alpha over 2, and in this one, they put the alpha over 2 before the nu. So this text, he puts the alpha over 2 first, right? It just depends on the author's times sigma hat times the square root of x0 prime c x0. Okay. So this is your 100%. And then you could also do a prediction interval. He doesn't even bother with it here. Okay? Okay. This x0 prime c x0 does correspond exactly let's see, does that correspond exactly with what we had before? Yes. It turns out that this thing does correspond exactly to the x minus x bar squared over sxx. In simple linear regression, this equals in simple linear regression to 1 over n plus x01 minus x1 bar squared over sx1 x1 in simple linear regression when k is equal to 1. Okay? This term right here corresponds exactly to that. Okay? And so the prediction interval you could obtain by adding 1 to this x0 prime c x0. All right? So it's exactly that thing. Right? Okay, in case k equals to what? What was the confidence interval for beta j alone? If I just take this was for the mean response. We always had a 1 here at the intercept and so on. But I can take any vector here, all right, and talk about 100 times 1 minus alpha percent confidence interval. All right. So if I take all zeros except the 1 for corresponding to beta j, then I also get the 100 times 1 minus alpha percent confidence interval for beta j, and that is beta j hat plus or minus t alpha over nu sigma hat times what we said was cjj, this square root of cjj there. Okay. Okay. And this is what's called the standard error of beta j hat. That's what's called the standard error of beta j hat. Just the estimate of the square root of the variance. In other words, I take the square root of the variance, which was right here. I didn't say what this was, sigma squared cjj. Okay? I take the variance. I didn't finish that up. This was the variance here. So standard error means I take the variance, I take its square root, and then I replace the sigma by sigma hat. Okay? And that's called the standard error. If I take the square root of this, I call that the standard deviation. If I take the square root and replace sigma by sigma hat, I call it the standard error. All right? That's the meaning of that terminology. Now you're becoming statisticians. You know what standard error means. Okay. Should we take a 5-minute break? Okay. Why don't we do that? I'll come back and do a little bit more of the F-test, but then I want to get into the general linear model. Okay. Extra sum of squares method. Okay. Yeah, the next page we need to do, we're going to get some heavy calculations, so you're going to need to catch your breath. Okay. Yes.